Can you say that one more time?
So on this slide, so if I have a base, which of these two species is going to react with a base?
Jeff?
The acid. So which one of these two species is the acid?
The HF.
The HF, correct. So if I react it with the base, my hydrofluoric acid concentration goes down and my fluoride ion concentration goes up. So why does this fluoride ion concentration go up? Addison, can you say that again?
It's going into solution and it's not reacting with the base.
Right, so when I do this reaction where I've got the OH minus reacting with the HF, it's going to take the hydrogen off the hydrofluoric acid and combine it with the OH to form water, but the fluoride ion goes into solution and that concentration will go up. So if I add a base, it's going to react with the acid. And so we see that the HF concentration goes down and the F minus goes up. And then if I do it, react it with an acid, my fluoride ion concentration goes down and my hydrofluoric acid concentration goes up. So I should say to myself, if I have the choices of HF and F minus, which of those two components will combine with the hydrogen ion? Well, this HF already has a hydrogen ion, so it's not going to absorb any more. But this F minus is the one that can absorb that hydrogen ion and become HF. So the HF concentration goes up and the fluoride ion concentration goes down. So that's kind of schematically what you see down below. So I have equal concentration here. When I add my base, I get the HF concentration goes down and the F minus concentration goes up if you sit and count the little spheres. So we have a visual of how that's going to happen, but now we need to do some actual, we have a clicker question. Okay. Okay, what do you think? So which graph represents buffer after the addition of strong acid?
C.
C. So my strong acid is going to react with my conjugate base. So my conjugate base concentration is going to go down and my weak acid concentration is going to go up. So by adding a strong acid, I've altered the ratio between my weak acid and my conjugate base. And so my conjugate base is the one that reacts with the strong acid and it produces more weak acid. Okay, so here is a situation where we have acetic acid and sodium acetate and the pH is 4.74. So I know that I'm at the pKa right now. How do I know that the pKa for acetic acid is 4.74?
Is it because of the chart? Or did it have something to do with the chart or no?
No. What do you get? So which of these two components would be in the numerator if I was doing the Henderson-Hasselbalch?
NaCl2H3O2.
Right, the sodium acetate's in the numerator. So 0.3 molars in the numerator. What's in the denominator?
0.3 molar.
0.3 molar. So what's the mathematical result of the log of 1? 0. Right. So I know that the pH equals the pKa right now when those two buffer concentrations are the same. Okay, so I've got this buffer situation. So now I'm going to take it and I'm going to add some acid. So when I add 0.02 moles of acid, which of these two components is going to react with the acid?
The
Sodium.
NaCH3O2.
Right, exactly, my conjugate base. So the salt of my conjugate base, this one is going to go down by how much?
0.0.
Right, it's going to go down by 0.02 moles, and my acetic acid is going to go up by 0.02 moles. So there we go. And so how did I get this number now? Where did this 4.68 come from?
When
You did the ratio again, like when you did the molarity, the
What's the name of the formula?
hydrogen one,
What's the name of the
sodium
formula?
acetate.
What's the name of the whole formula? What's the name of the equation that we're using? What's the name of the equation we're using?
Oh, Henderson-Hasselbalch.
Yes, Henderson-Hasselbalch. So we're gonna, we're gonna Henderson-Hasselbalch that one. So I've got the sodium acetate will be in my numerator, and my acetic acid will be in my denominator. So that means, what was the sign of the result once you did the log of that ratio? Was it positive or negative?
Negative. Negative.
It was negative. So how do I know it was negative?
Because it's smaller in the numerator.
Right, exactly.
and
It's
more-
smaller, correct. It's smaller than,
It's happening.
hey, you're back. You're good, we can still hear you. So the log of the ratio of these two was negative. So that we went from 4.74 to 4.68. Does that make sense that the pH went to 4.68 when I added acid? Yes. So I've become more acidic. Okay, so same situation if I'm going to do a base. Now in this situation, my acetic acid goes down and my sodium acetate goes up. So we're going to do what we call a bar chart, and it'll be before, what we added, and what remains. And when you do a bar chart, you have to do a bar chart in moles. So we have some molarity values over here, but we actually are going to use moles when we actually do the concentration. So once we add or subtract the moles of acid or base, and then we're going to redo our Henderson-Hasselbalch to get our pH. Oh, pretend you don't know that.
What?
Pretend you can't see the answer. Okay, so I've got chloroacetic acid and I've got sodium chlorate. I'm going to add 0.05 moles of HCl, and the pH is going to go down a little bit. So, oops. So what's my question? Okay, so the question is, which species is going to react with my HCl? So why is the answer chloroacetate?
Because that's the base.
It's more specifically what kind of, what base? What word do we put in front of it? Say that again. Yeah, the conjugate base, right. So remember, we have our choices of our weak acid and the conjugate base. So you can always tell by the words. If this is the chloroacetic acid version is only going to react with the base like sodium hydroxide. If I've got the chloroacetate ion, which is my conjugate base, that's the one that's going to react with the strong acid, which is HCl in this case. So pay attention to the fact that we're adding strong acid, which is HCl, and the strong acid's not going to react with something that's already an acid, the chloroacetic acid. It's going to react with the thing that's the conjugate base, which is the chloroacetate ion. So if we were doing this, we would see that the chloroacetate ion concentration would go down and the chloroacetic acid. I might lose my internet connection here. Okay, hopefully we're still good. Okay, so we've done this situation many times. So we have acetic acid and sodium acetate. So now what we're going to do is we're going to add a little bit of base to it. So across the top of our chart, now we're going to have our acetic acid, we've got our acetate ion, and in this case, this OH is what we're going to be adding to our buffer. So we're going to set up our equilibrium, so it's going to look like this. So we've got acetic acid, so this hydrogen from the acetic acid is going to combine with the OH that I'm adding, and it's going to become water, and then my acetate ion is going to go in solution. So when I start, I have those two. I've got 0.3 moles of each one of those. So remember, this has to be in moles. So now I'm going to add some base. And in this case, I'm going to add 0.02 moles of base. And the question is, what things will go, concentrations will go down and what concentrations will go up? So what's my answer?
The acid will go down. Well, the first two reactants will go down.
Right, exactly. Right, the two on my left are going to go down. And then my acetate ion is going to go up. So notice it's on the other side of the equilibrium arrow. So when I'm done, I'm going to have 0.280 moles of acetic acid, all my bases used up, and I'm going to have more acetate ion than when I started. So I've got 0.280 moles of acetic acid and 0.320 moles of acetate ion. So now I can use this last R row, this remaining row, I can use this and plug it into the Henderson-Hasselbalch. So why does the chart have to be in moles? Let's come up with an answer to that question. What do you think? Why does it have to be?
Is it so if the like volume changes, it's easier to calculate?
A little more than that. So why did I call this the stoichiometric section of trying to solve the problem?
Because you might have to go to grams.
No, we're just going to stay in moles. So when we do stoichiometry, we're going to be we care about the mole ratios between things. So when I'm doing these buffers, I have to pay attention to how many moles of components are there. So I can mix different volumes with different concentrations as long as I can pay attention to the number of moles that's there. So when we do this, absorbing the number of moles of acid and the number of moles of base are the ones that we're concerned about when we go to adjust the pH of this buffer. So we have to have the moles of acid and the moles of base to be able to see how we're neutralizing them. And then the molarity is of less importance until we go back to do the Henderson-Hasselbalch. So remember, our acetate ion goes up because we've gotten rid of the hydrogen off of the acetic acid, and that left acetate ion in solution. So it's the same thing as our Le Chatelier's principle. So we decreased the concentration of the acetic acid, and we increased the concentration of the acetate ion. Okay, so our last step is to do Henderson-Hasselbalch. So for this one, we already have that the pKa is 4.74. And so now we need our conjugate base in our numerator and our our weak acid in the denominator. So do the math on that one real quick. Let me see what you get. What do you get?
4.8.
4.8, you got it. So we saw this time that our numerator was bigger than our denominator in our fraction that we take the log of. So we know that that value is going to be positive. So we know we're going to go 4.74 up to 4.8. Okay, awesome. So we have seen how we can adjust the pH of a buffer by adding an acid in this case. Okay, so let's look at this one. So we've got acetic acid and acetate ion with a certain number of moles of acetic acid, a certain number of moles of acetate ion. And in this case, we're going to be adding a little bit of base. And we're going to be adding 0.02 moles of base. So how are we going to approach this problem to solve it?
The bar chart.
Yep, and we need to start with the bar chart. So what is going to react with the base?
The acid.
The acetic acid, right. So our strong base is going to react with our weak acid. So our weak acid concentration goes down and our conjugate base concentration goes up. So if we work on that a little bit, we should get something that looks like this. So we started off with 0.024 moles of acetic acid and 0.012 moles of acetate ion. And I guess I did a little bit of rounding with this one. So 4.8 was my pKa. And so my acetate ion goes down, my acetic acid goes up, and here are my two new concentrations for my moles. So I need to do my Henderson-Hasselbalch as my last step. So I can calculate the molarity of each of the two. So when I do it, I'm going to get the numerator of 0.032 molar and the denominator is 0.004 molar, because I think these are both in a liter. Oops, there's a little. So when I do that one, I should get about 5.69. So in this situation, it just said we were in a liter. But if you had two different volumes from two different solutions, you would want to add those two together, and that would be the denominator. So good. So so our pH is now 5.69 after we've added a little bit of base to it. Okay, any questions on that one? No, you good?
Nope.
Gab, you good? Okay.
Yeah. Sorry, my dogs are barking. So.
Oh no, we don't care. It adds some entertainment. Oops, let's go back. Okay, so we have a new situation. This is a little bit big on my screen here. There we go. Okay, so we have a new situation and we're going to have 200 milliliters of a solution that's got 0.5 moles of acetic acid and 100 milliliters of something that's 0.5 molar sodium hydroxide. So this is very similar to the stuff that you're doing for your problem, your homework problem. So I gave you the Ka for acetic acid. So set up the equilibrium, look at what the base is going to neutralize, and then do our Henderson-Hasselbalch. So that's our plan. Okay, so let's set up our chart. So we're going to have our moles of acetic acid. So where did that moles come from? Where am I going to get the moles?
It's 0.5.
So how am I going to, so what am I going to use to calculate those number of moles?
It lists the moles of the acetic acid.
Oh, did I? Wait, I thought I gave you, I thought I gave you volume. Oops. Oops. That. Okay. Oh, I did give you moles. Okay, darn. Oh, the sodium hydroxide, that's the one I gave you in the volume. Okay. All right, so I gave you the number of moles of acetic acid. So how many moles of base do I have?
Well, do you want me to tell you how to do it, or
Yes, tell me how to do it.
you take your moles, or your molarity, and multiply it by the liters?
Exactly. So the molarity times the liters in this case. So that was going to give me moles of hydroxide. Can you guys see my little annotation at the top in blue?
Yes.
Okay. So that gives me the number of moles of hydroxide. So go do the math, tell me what you get.
I got 0.05.
Yep, 0.05. So what's going to...
Wait, are those numbers?
I think we should, I like to fix this one a little bit. I like this up here. I like this better. I kind of liked it the way we did it on the other slide a little bit better. Like I liked this one as like that.
Yeah.
I think I like that better. And then I liked
Did
this
we
as
start
well.
with 5 of the acetate ion?
Does it say that it's a, so we should have,
It only gave us base and acid numbers, not the times for things.
I think the word that needs to be added is this is an acetic acid, that this is, whoa, that's not what I want. That this is an acetic acid buffer. I think that's the word that we need to add to this. So when there's an acetic acid buffer, then that's going to have both that. So if the word buffer is in there, that means that the acetic acid and the acetate are both 0.5. Because you're right, if I just said acetic acid, then that would be a 0 on the other side. But that's not what I mean to do for this problem. So we should have that this part should mean that there's both the moles of acetic acid and acetate ion are. Okay, that makes sense. So that's why when we fill in our chart on the next one that we've got both of these values are the 0.5 because it is a buffer. So that's what we wanted it to be, as a buffer. Okay, all right, I like this better. All right, so we've got our acetic acid is going to go down, our acetate ion goes up, and so now we have 0.50 moles of acetic acid and 0.55 moles of acetate ion. So now I need to do the Henderson-Hasselbalch. So I need to go and convert these into liters, meaning to molarity. And so I should get 0.55 over 0.50. And our very last pH will be 4.84. And I'm recording this one today too, so you guys can go back and look at it too. Did anybody go and look at the previous video from the other class?
Yeah, the ones that you like save to the cloud like open up, but the other one, the first one, still like it downloads now, but I can't like open it. I don't know why.
Okay, so you like the one that's to the cloud better?
Yeah, it just like opens up a tab and plays it.
Okay. Because at least when I tried to do it on my phone, it made me try to download that whole entire video when I did it to the cloud. But sorry, it's getting really loud in here. My husband's on his meeting today, this morning too. So sorry about that. If you can hear him talk about chemistry. Okay, so let's do this one where we're going to have our buffer, and this time we're going to be adding a little bit of acid. Okay, so let's work through this one. So our concentration, we'll ignore the answer to the question right now. So in this case, we've got formic acid. So I gave you the Ka is 1.77 times 10 to the negative 4. So your pKa is 3.75. And so in this case, I need to do the concentration of my sodium formate and the concentration of my formic acid. I need to get the number of moles of each of those. So remember, molarity times your volume will give you the number of moles. So let's look for a second on our, let's look at our equilibrium here. So why did I set my equilibrium up like this?
Because the sodium is a spectator.
Okay, so sodium is spectator, so it's gone.
So is chloride.
So, but why is my hydrogen ion on the side with the formate when the last time my hydroxide ion was on the side with the acid? So why is this hydrogen on the product side this time? Can you speak up a little bit?
I don't really know. Is it because it comes off the HCl that's added?
More than that, though. So remember, when I have a buffer, the two components of my buffer are this one and this one. Those are the two components of my buffer. And so the acid reacts with the conjugate base. So I need the acid and the conjugate base to be on the same side so that when I do the math of it, both the acid and the conjugate base will be going down. They'll be the minus mole values, and my acetic acid side will be going up. So you want to make sure that you write this equation to reflect whether your buffer is going to be in the presence of an acid or a base. In this case, it's in the presence of an acid. So my HCl is going to react with the acetate ion. Is that completely clear?
No, but whatever.
No, don't do that.
Could
I'll
I have just said like the NaHCO2 plus HCl is like the equilibrium sign to HCO2H? Like just written it out the full way rather than taking things out?
Yes, and do you want me to rewrite it the other way so that the sodium acetate and the HCl are on the left side? Is that how you want me to do it?
No, you're fine. I can visualize that. I just wanted to know if that was okay. Like, I
Yeah,
didn't have-
absolutely. Yeah, if you don't like the fact that I drop out all the spectators, just put them in.
Okay.
Yeah, it doesn't matter that the spectators are there. It's perfectly fine because it's not going to change it. And actually, if you like it that way, and if it helps you do the Henderson-Hasselbalch that way too, go ahead and leave them in.
Okay.
So when we're reading the equation, like how do we know it's going to be set up like this? Like how do we know that the product side is going to be on the left-hand side compared to being on the reactant being on the...
So actually remember, so this is an equilibrium, so it does, so left and right don't really matter. But the important thing is when I go to the Henderson-Hasselbalch, I have to pay attention to make sure that that this one will be in my numerator and this one will be in my denominator. So it doesn't matter where they are in my row. I just pay attention to the fact that my conjugate base goes in my numerator and my weak acid goes in my denominator. So left-hand side, right-hand side doesn't matter. But as long as I know that my conjugate base, that this value is in the numerator and that value is in the denominator. So I can rewrite it, switching the left and the right, but you get the exact same answer because that's all I care about is I'm going to look here, I'm going to look for my conjugate base, that'll be my numerator, look for my weak acid, that will be my denominator. And the most important thing is that your acid, your strong acid, is reacting with that conjugate base. That's the most important thing. And you see that your moles of conjugate base are going down and the moles of your weak acid are going up.
Okay.
So go ahead and finish the problem. Go calculate the pH for the rest of this buffer.
Negative 0.347.
Yes.
Do we have to put it back into molarity?
Yes, so you can put it back into molarity, and I'm going to show you a quick way of doing it so that you can so that you can get your concentrations correct without having to plug it into molarity again. So when we do this, we'll see that the numerator is the 0.0075 moles. And then the 0.1725 is the denominator. But you see that the numerator and the denominator are both, one's divided by 0.05 and the other one's divided by 0.05. So what you end up doing is you end up seeing that this value actually drops out. So technically, you can put in the moles in the numerator and the other moles in the denominator, and without having to divide and calculate the concentration before you do that. As long as these two values are the same, you're basically multiplying by 0.5 and dividing by 0.5, which ends up canceling them out. So technically, you really should be calculating the concentration, but mathematically, those volumes drop out, and so it's moles over moles when you look at it mathematically. So this is the shorthand way of doing it. Please write it out so that I see that liters is there, but you can just drop them out and just do the actual mole value. Does that make sense?
Yes.
Again, I took a long description for something that was supposed to be short. Okay, so this time our denominator or our numerator is smaller than our denominator, so the log of this value is going to be negative. So our 3.75 is going to go down to 3.40. So we've done examples of a buffer with an acid and several examples of buffers with a base. The technique is exactly the same. You just need to decide which species will the strong acid react with or which species will the strong base react with. Are we good so far?
Mm-hmm.
Okay, all right. Oh, all of those little things stay. So we did this already the other day, so we don't need to go over this too much. But so we did our titrations. We see we're going to do the equivalence point. So when we did our titrations, we saw the equivalence point was the center of the steepest portion of the curve. And in this case, we added a strong acid and a strong base. So we had a very, very strong or very steep portion of the curve. And in this case, if we did phenolphthalein, it would be colorless down here. And then as soon as it turned a little bit basic, it would have turned pink. And we did this homework problem where we could see what was present. So right here in the middle, it would be equal amount of acid and base. A little bit beyond that was more base. And then less than that, we would have more acid. And then right here in the middle, we would have equal amount of weak acid and conjugate base. So we call this the half equivalence point. So the concentration of the weak acid is equal to the concentration of the conjugate base. So remember that that ratio gives us a log of 1, which is 0. So the pH equals the pKa at the half equivalence point. And we did that in lab yesterday. Okay, got it. We did, and this was our homework problem. So as we go through and try to titrate a weak acid, we're going to see that the steepest portion of the curve gets smaller and our pH is no longer 7 at the equivalence point. And depending on whether it's a weak acid or a weak base, that number will go up or down depending. So we'd already titrated weak acid. So I've got these 4 plots. So I want you to figure out which one is, let's see what my choices are. I guess I didn't have any choices. Okay, so our choices are strong acid, strong base, weak acids, weak acid with a base, and a base titrating an acid. A base titrating with an acid.
You want us to identify them?
Yeah, so let's do some process of elimination. So which ones are the weak acids?
Remember the second one? The second one on the top row.
Yep, so number 2 is a weak acid. And is that a weak acid titrating with a base? And how do
Yes.
I know?
Yes.
Yes. So notice when we did this titration, especially like when we did in lab yesterday, we started off here on the far left-hand side. So the x-axis is the volume that's being added. So if I'm starting off really acidic down here, pH 2 or something, and I'm adding base, remember I'm going to start heading to the right, and I'm heading up towards the passing the equivalence point up to basic at pH 10 or something. So I can always tell that I'm adding base with number 2 because my solution started off at a pH 2 and I worked my way up to pH 10. And so what about the number 3 down here on the bottom left hand corner? Is that still a weak acid? Mm-hmm. That's still a weak acid. And am I titrating it with an acid or a base?
Yes.
Yeah, I'm titrating it with a base. So this time I'm starting off as pH 5 and I'm going up. My equivalence point is about pH 7, and then I'm going a little bit more, and then I'm ending up at only like pH 9 or something. So this is this shape for number 2 is different than the shape for number 3. So these ones that are in diagonal are definitely different. They're both weak acids. So we'll talk about them again in a second. So what about this third one on the bottom right-hand corner?
Is that the weak base with an acid?
Yeah, exactly. So this is my weak base and I'm adding an acid. So how do I know I'm adding an acid? Sorry, say that again.
It's like getting more basic at the principal zero, like a pH of 0.
If my pH is going down, what am I becoming? Right, I'm becoming more acidic, right? So I'm starting off at pH 10 and I'm becoming more acidic. I'm titrating through and then I'm ending up at pH 1. So this last one is I'm adding a strong acid when I titrate this one. So I'm starting off very basic and I'm titrating with a strong acid. So this is still going to be a weak base right here, but because it's still's got, a small steep changes, those the equivalence points, that region is a small region compared to this one at the number 1. So this is still a weak base, but I'm titrating this weak base with an acid. I'm finishing up at the end of my titration at pH 1. So this number 1, what characteristics do we see in that one that's different from number 2 and number 3?
That's strong acid.
Right, this is a strong acid and a strong base. So how can I tell for sure?
Well, that would start at 0, and then it has a huge change in the pH.
Exactly. Right, that's the most important thing, is this really, really steep change right here. Just 1 or 2 drops and it will just go shooting right up in pH. So it looks a little less dramatic on the plot, but when you're physically doing it, it'll go from, one drop will make it just go from a pretty acidic solution to a really basic solution in 1 or 2 drops. So all 3 of these other plots are all buffers, and typically they're going to be weak acids or weak bases. And so where is the buffering region? Like maybe if I look at number 2, where would the buffering region be?
Mm,
About what pH would that? I think each of these is 1.
9.3.
So where do I want the buffering region to be? Up here at the equivalence point?
oh,
Oh no. Maybe down a little bit, or like that, where it comes around.
So remember when we did we looked for our equivalence point in our plot yesterday, and then what did we look for once we found that this was at 25 milliliters?
The half.
Right, so we looked for the half equivalence point. So this region right here is where the most amount of buffering is going to take place. So this region right here, is got the most buffering. So how do I know that that's got the most buffering? Oops, I'm just going to type that in so that you guys don't have to read that silly handwriting. So how do I know that?
Is it because it takes a while for the pH to go up?
Exactly.
Gradual?
Exactly. So that means that I can add 5 mils, 6 mils, 7 mils, 8 mils of sodium hydroxide, and the pH is only changing just a little bit. So that's the whole definition of buffering. So when I can add some sodium hydroxide without it changing very dramatically, that's buffering. And so over here at the equivalence point, that is not buffering. That is like a dramatic change with only 1 or 2 drops. So that's not buffering up here at the equivalence point. The buffering is going on down here where it's not changing very much. And then it's going on again up here a little bit. Again, up here where there's not very much, where it's starting to flatten back out again. So you can get buffering at both of those 2 places. Does that make sense? Yes? No?
Yes.
Yes.
Sorry.
Okay, we're saying yes. So what about okay, so what about the answer to this question? Weak acid. I like it. It's C. So what's different about this one?
This one has a lot of equivalence points. buffering areas.
Exactly. So it's got 3 little flat regions that are going to be the places that it'll buffer. And so if I see this little step that's going on here, each of those steps is from one of those hydrogens coming off. So phosphoric acid has 3 hydrogens that can come off when I add base. And the pKa, like that's written right there, is going to be the middle of all these flat regions. So this first one says the pKa is 2.2, so it's going to be right there in the middle of this nice flat region. And there's our peak. Oh, let's draw it down here. There's our pKa 2. And so our pKa 7 is going to be perfectly right in the middle of that one. And if I let it go, this one would be somewhere up there in a flat region up there, if we continued this up there a little bit. So each of these pKa regions are in the middle of this really nice big buffering region. So there's another one right there, beautiful, and then another one, really nice one up there like that. So each of the hydrogens that comes off gives you a little change in the concentration, steep portion of the curve. The first one's actually happening over there. And then, but you get these really nice big buffering regions. And so where is the biological pH in this plot?
Would it be 8?
Say that again.
Would it be 8?
A little bit, yeah, a little less than 8, more like about 7.4. So this 7.4 region right here, this is exactly physiological pH. So why was that important?
That's probably a quiz question.
What?
I said because it's probably going to be a quiz question.
It is going to be a quiz question. You can be prepared for that one.
Oh boy.
You have to know when she goes to depth on something, it's just going to be a question. You might as well start.
Exactly. See, you guys know me so well. I'm going to beat this one into your head.
Mm-hmm.
So, why physiological pH? Why is this good that physiological pH matches this nice little beautiful flat region of the phosphoric acid titration curve?
Because stuff in our body phosphorylates, so we're probably getting buffer.
Maybe a little more than that.
I got nothing. That was nice to understand.
Between both of the other buffers.
So our bodies don't change in pH too much.
Say that again, Addison.
So our bodies don't change in pH too too drastically, too quickly, it'll like throw off your what's it called?
Edge balance.
Mhm.
H, I'm pretty sure. I think it's no, I don't know. I can't think of it.
How's that? How's that for an answer?
Great.
Yes, that's excellent. We're learning about metabolic reactions right now.
So phosphoric acid is one where there is a big buffering region at physiological pH. What was the other compound or the other equilibrium that we talked about that also did a had buffering at physiological pH? Say that again.
Bicarbonate.
Yep, bicarbonate. There, how's that? So the two examples we actually had three examples. So we had the bicarbonate buffer system, we had phosphate buffer, and the third one was proteins. Also do a very, very similar thing, except instead of having a little titration curve like this, where you use the entire protein to absorb an acid or a base. But these are extremely important in preventing acidosis, and alkalosis is the other one. Oops, I gotta get out of here. Okay. Okay, that was our last slide for today. Thanks for hanging in there, guys. Okay, so quiz for tomorrow. I'm going to post this in as many ways as possible, but all of the annotations are done for the OneNote version of the notes as well. Keep working on your homework problems so you guys will be able to do the homework problem that you were assigned. So let's maybe do our homework problems before we take the quiz. That might give you guys a good little refresher review as we go through everybody's. You'll see the pattern. There's, pretty much there's a lot of them that are pretty similar between everybody's problems. So the first one might take a little longer, and then everyone else's will go pretty fast.
Is there going to be a practice quiz? Is there a practice quiz actually uploaded on D2L?
No, but I will put one up in just a few minutes. So you guys will have a practice quiz for this chapter.
Okay.
Anything else you can think of?
Are you just meeting on Zoom tomorrow morning?
Yeah, we're just going to meet on Zoom tomorrow morning, and each person can do their homework problem so that everyone will have that portion of the homework done, and it'll be used as a good little review for the quiz. Then I'm going to have everybody keep their camera on and their microphone on and then you guys are going to take the quiz, and then you're going to upload your answers to me. I'll probably do a Dropbox, or I'll do just you guys can just email it to me. And then after you're done emailing it to me, then we'll go over the quiz, and then I'll answer any questions you guys have about the exam on Tuesday.
Okay.
But the good thing about this exam on Tuesday is all 3 chapters are equilibrium. You do the exact same thing. So you'll go back and look at chapter 17, and you'll say, this is like so easy, like you know, so because by the time you get to 19, you've done it so much that the information flows really well, and you'll be able to studying for it will be a lot less challenging than some of the other exams that we've done in the past. So okay, any other questions? No?
Nope.
Okay, so any questions, you guys can just email me or whatever, and then I will see you guys tomorrow.
All right.
All right.
Bye.
Bye.